On this installment of MatHAMMatics, we're going to take our recently learned quadrilateral definitions, and we are going to learn how to prove some quadrilaterals. Well, welcome to this edition of MatHAMMatics. As promised, we are going to be looking at coordinate geometry quadrilateral proofs. So the last time that we were together, we did some proofs with triangles. And so today we're going to use the definitions that we learned about for different types of quadrilaterals, and we're going to start to prove those things. In example number 1, the first quadrilateral that we're going to be taking a look at here is the parallelogram. Remember, a parallelogram from our definitions possesses two sets of opposite parallel sides, and thus we're able to learn a handful of other things about their characteristics, right? The opposite angles, so in each corner, you draw us a parallelogram here. When you have a parallelogram, not only do we know that the opposite sides are parallel to one another, we also know that the opposite sides are congruent to one another. We know that opposite angles are congruent from one another as well. Okay? So here is all of the different characteristics that we can learn or utilize about a parallelogram. And so when we begin to think about these proofs, we want to start to think about what ways can we use the characteristics of a parallelogram to our advantage. So first things first, let's plot our points. So point A is situated at -1, 1. B is at -3, 4. C is at 1, 5. And D is at 3, 2. And so here is the parallelogram, or at least the potential parallelogram that we would like to prove. But what's going to be really important for us in order to determine whether or not this is a parallelogram? Well, we need two sets of parallel sides, right? We also need two sets of congruent sides. So can we prove here that we have a pair of parallel sides on each end of our parallelogram, and can we prove whether or not they are congruent? Well, we can begin, right? Parallel sides, right? What do we know about two lines that are parallel? Well, two parallel lines are going to have the exact same slope. So does the slope of AB equal the slope of DC? Let's figure that out. The slope of AB, the rise here is -3. The run is 2. The slope of DC, the rise is 3. Again, in the negative, right? If we're going from C to D, it goes down 3. The run is 2. And so look at that. Right away, we can see we've got the same slope. And so we can prove, at the very least, that AB is parallel to CD, right? So there's one step down, all right? So we got one of the sets. Let's take a look at the other set of parallel sides. Are these, in fact, parallel? What's the slope of BC? The rise is 1, the run is 4. What about AD? The rise is 1, and the run is 4. And so again, here we see the same slope. And so we can say that BC is parallel to AD. So we're halfway done, right? We've got our two sets of parallel sides. So can we then prove that they are congruent? Well, let's take a look at the distances for AB, for DC, for BC, and for AD. Well, since each of these has the same slope, we already know, right, that the distance for AB is the square root of the run squared, right? So there's the run plus the rise squared. Square root of 4 plus 9, square root of 13, right? There's AB. If we were to plug the information for DC in, we would get the exact same thing, right? The distance of AC is also going to equal the square root of 2 squared plus negative 3 squared, or the square root of 13. And so now we can see not only are they the same slope, but they're the same distance. Lastly, we can check and make sure that that's going to be the case with BC and AD. And again, the distance for BC has to equal the square root of 1 squared plus 4 squared. The distance of AD is going to equal the square root of 1 squared plus 4 squared. And in each of these cases, we're looking at the square root of 17. And so we've got the same distance. And so now, because we have two sets of parallel sides, and those same sides are congruent, we can now say with certainty that the quadrilateral ABCD is a parallelogram. So as we're starting to look at these different quadrilateral proofs, the big thing is, can we compare the definitions that we found for parallelogram or for all of these other types of quadrilateral and determine then that we have that particular shape? Again, utilizing the same techniques that we did here for the triangles, right? Stuff with distance, stuff with slopes. Flip my head over to this side here for this one. So we've got quadrilateral DEFG. We know that the vertices are at 3, 4. Each 6. 9, 9. And 4, 7. Can we prove that this is a parallelogram? Well, let's use the same techniques that we did before. In order for this to be a parallelogram, we would need to prove that DE is both parallel to FG as well as DE is congruent to FG. We would need to prove that DG is parallel to EF as well as DG being congruent to EF. So let's test the slopes. Slope of DE versus the slope of FG. Well, for DE, the rise here is 2, and the run is 5. For FG, the rise is 2, and the run is 5. All right, so those are definitely parallel, right? Because we've got the same slope. Utilizing the fact that these rise and run unsimplified, right? These came as simple as they get. And if you plugged these into the distance formula, right, the distance of DE and the distance of FG, these would be the same. You would have run squared plus rise squared, and both would match up identically. And so we would be able to say, oh, okay, this is going to be the square root of 29, this is going to be the square root of 29. And so not only are both of those parallel, these are also congruent. So we've been able to make this claim, and we've been able to make this claim. So can we repeat this process with our other two sets of sides and then determine for ourselves we have a parallelogram? Slope of DG that's a slope of 3/1. And the slope of EF is 1/3/1. So in both of these instances, we have the same slope. Therefore, we can prove they're parallel. Lastly, if we plugged these into the distance formula, just like we did before, right? The distance of DG is going to equal run squared plus rise squared, right? Which is just the square root of 10. And if we did the distance of EF, we find the same thing, right? 1 squared plus 3 squared, square root of 10. These are congruent. And so now we can say with certainty that we have two pairs of opposite, parallel, and congruent sides. Therefore, DEFG is a parallelogram. Let's check out a couple other proofs here. So a quadrilateral ABCD has vertices of 2, 3, 10, 3, 10, -1, and 2, -1. So let's plot those. 2, 3. We've got 10, 3. We've got 10, -1. And we've got 2, -1. Prove that this quadrilateral is a rectangle. So a rectangle, if we remember from our definition, is a parallelogram, but it's a special type of parallelogram where the opposite sides of those are certainly still congruent. They're still parallel. But now the big difference, right, is that each of these meets at a 90-degree angle, right? So that's what separates the rectangle from any old generic parallelogram. So let's see if we can get ourselves a proof here for this rectangle. What are the things that we're going to need to prove? Well, we need to still prove that the opposite sides are congruent, right? We need to prove that the opposite sides are parallel still. So AD still has to be parallel to BC. AB has to be congruent to DC, and AB needs to be parallel to DC. But additionally, we have to prove that there's a right angle involved. And so when we're looking at these slopes, we also need to prove that AD is perpendicular to, say, DC, and that BC is perpendicular to AB. Any combination of these things would be sufficient. Now again, this may feel like it's an extra step, but it's not really all that extra, because in order to prove that we have parallel sides, we already have to evaluate the slopes. And so when we look at the slopes, we can simply be looking for, not only do we have the pair that matches up as the same slope, but when we look at the two that meet, are they in an opposite reciprocal relationship, right? So that's kind of the key as to what we're looking for there. So let's take a look at our slopes here. So the slope of AD. Well, what do we notice about the slope of AD? The rise there is 4, but what's going on with the run? The run is 0, right? And so we have an undefined slope. Well, that's interesting. Is that also the case with BC? Let's take a look. Right, BC also has that same rise of 4 and that same run of 0. And so both of these produce undefined slopes. So those are in fact parallel. Well, what is the perpendicular slope to something that's undefined? Well, of course, that's a slope of 0. And we can clearly see this from the diagram, but we can prove it to ourselves. The slope of AB or the slope of DC, both of them are going to have a rise of 0 and a run, not a 4. But we're going to have a run of, what is that, 1, 2, 3, 4, 5, 6, 7, 8. And so we not only have our parallels here, but these two are perpendicular, right? And so we have proven 2/3 of what we need to prove. And then from here, it's pretty straightforward, because we can just plug our rise and our run into the distance formula and confirm that we have congruent side lengths. AD and BC have the same rise and run, which is 0 squared plus 4 squared, right? Which is, of course, just the square root of 16 or 4. Or in these cases, right, because we have a vertical and horizontal line, we can actually even just count out what's going on, right? We can do, we can already see 1, 2, 3, 4 as our vertical, 1, 2, 3, 4, 5, 6, 7, 8 as our horizontal. And so we've got ourselves obvious congruent sides. And so all of these conditions now are met. We have our congruent sides, we have our parallel sides, we even have the perpendiculars ensuring us of the 90 degrees. And so we can say that ABCD is a rectangle, right? So that's kind of the one added piece to the rectangle. So for number 4 here, it would be the same kind of idea. So I'm going to leave this one for you guys to try later and take a look at a different type of quadrilateral. Here, QRST has vertices at 6, 7, 11, 7, 8, 3, and 3, 3. And so this is T, this is Q, this is R, this is S. And we want to prove this is a rhombus. Now remember, a rhombus is a parallelogram that all four sides are the same length. And so that's the key that we're looking for. Are all of these sides the same length? So does QR, right, line up in congruence with RS, in congruence with ST, in congruence with QT, and still are QT and RS parallel, are QR and ST parallel, right? So these are the questions we're trying to prove. Well, let's look at the slopes first. The slope of QT, rise here is 1, 2, 3, 4, run is 3. Right, so we've got ourselves 4/3 as the slope there. The slope of RS is 1, 2, 3, 4, 1, 2, 3. So look at that, exactly the same. We've got ourselves parallel lines, beautiful. What's the slope of QR? Well, that's a horizontal, so the slope is 0, right? Slope of ST, also a horizontal, so the slope is 0. And so we can see now too that not only is QT parallel with RS, but QT is also parallel, QR is also parallel with ST. Well, let's look at the distances. We can tell that the length of QT and RS is going to be the same. Right? If you plugged both of those into the distance formula, we would be able to find that those are congruent. Right? If we plugged QR and ST into the distance formula, what do we even need to? It's a horizontal, right? This is just 5 units. This is just 5 units. So we can tell those are the same. So does QT equal 5 units? Square root of run squared plus rise squared, well, 9 plus 16 square root of 25. Yes, it does, right? And so now we've been able to show that they're all congruent and that each of our pairs of sides are parallel. We can say with confidence that QRST is a rhombus. So in each of these situations, so long as we have the algebra to back up our statement, right? We have proof of parallel lines, proof of congruent sides. We can make these claims based on what we know about these properties and definitions of quadrilaterals. If you have any questions, please reach out.